Hello everyone, welcome to Tech-Lavya. Please like, share and subscribe.
The topic for today's lecture is interconnection of three-phase voltages. There are two types and we are going to discuss star connection here. Okay. Now in three-phase supply or in a three-phase generator, we have three identical windings, right? Now each windings has two terminals. One is called the start terminal and second one is called the finish terminal. Fine. So now suppose I connect the windings like, now if this is an R winding which is connected to load, then I require two wires, right? This is one, this is two. I require two wires for one winding, right? Similarly, I have Y connector. Again, I require two wires. Then I have B connector. Again, I require two wires. Correct? It means if I connect each winding separately to load like this, then I would require total 6 conductors or 6 wires, right? So basically we should work towards reducing the number of conductors. Otherwise, because the basic advantage of three-phase supply is that, right? It has lesser number of conductors and it is cheaper. Now, in order to do that, in order to reduce the number of conductors, new type of connection was proposed. The first is called star or Y connection and the second is called delta or mesh connection. Remember, we have seen such type of connections for our resistors in DC circuits, correct? But there we discussed about conversion from star to delta. But here we are discussing how these windings are connected together. So please now concentrate on the first diagram, this one. So here we have R winding and you can very well understand that one point, one end, they are connected together and that becomes a common, right? This is a common connection and that is called neutral. This point is called neutral. And then three separate conductors are taken out. So now how many conductors do we require? We require only three types of conductor. Correct? Now see, the current IL is flowing here. That is the line current, right? Now if you talk about the phase voltage or line voltage, phase voltage is the voltage across each phase. So this is phase voltage. And what is line voltage? The line voltage will be the voltage between two lines or between two phases. Correct? So phase voltage, if I want to denote phase voltage here, it will be the voltage between R and neutral. That is a common point. Please understand this. Okay. Now this is a balanced load. So I would say this is equal to another phase voltage will be at Y. But Y with respect to neutral. Again at B. B but with respect to neutral. This is the phase voltage. But if we talk about line voltage will be the voltage between two phases. So it is between R and Y, or it is between Y and B, or it is between B and R. Understood? So this is called line voltage and this is called phase voltage. Got it? Okay. I hope this point is clear to you. So now here we have a neutral point. Fine. Okay. Now what we are going to do is, see, here is our load and here is our supply. So now load is also connected in star fashion or Y connection. Fine. So here we have three loads and say these are connected at phases. So this is called phase load. So under balance condition, all the loads are same, correct? Identical loads we have. So ZPH I will write. Fine. So this is the R winding. So this R winding has to be connected to this load. So here we have a current called IR. Secondly, we have Y winding, correct? And here Y point is this, and here Y point is this, right? So we will be connecting this, and here current is IY. Fine, okay. Then we have to connect the neutral points together. So here we have connected neutral points. Then the last connection is IB. So this is B point or B phase. So what we will do is we will take out this here, and this is the B connection, and here the current which flows is IB. Okay, so this is how the supply is connected to load in star fashion. Now, which current flows through neutral wire? The sum of all currents, and that current will be flowing in the opposite direction. Okay, so we have IR plus IY plus IB. This is the current which flows through neutral wire. Understood? Okay, yes. So let us go ahead now. Now, let us start connecting this, but you must have noticed, see, this is R, this is Y. We are going to derive few things, okay, few expressions. So let us connect this together. Y is this, so Y has to be connected here, and then B, so B will be connected here. Okay, and let us denote all the currents. This is IR, this is IY, and this is IB. Now see, here we have not connected neutral wire. Why? We will discuss that now. So how do I represent the current? Now any instantaneous current will be represented by, now this is a sinusoidal current, so I will represent it by Im sin omega t. Similarly, through Y phase, I have Im sin. Now what is going to be the phase? Y winding is 180 degree behind R phase. So it will be omega t minus 120 degrees. Similarly, I have B phase, and B phase will be 240 degrees behind R phase. So here we have omega t minus 240 degrees. Correct? Now if I talk about the current which is flowing through neutral terminal, fine, that current will be the sum of all these currents. So the current flowing through neutral wire, yes, so the current flowing through neutral wire equal to, what is that current? It is the sum of all phase currents. Okay, yes, it means now when I add all three currents together, I will be getting the current flowing through the neutral wire. Now if you remember this discussion in our first class, first lecture, okay, we had similar kind of equation, but there we discussed about voltage, and here we are discussing about current. Otherwise everything is same. So what is the difference now? There we had VR, VY and VB, and we had a term called VM. Here you have IR, IY and IB, and you have IM. Otherwise everything is same. It means that when you add these together, whatever result was obtained after adding them, the result is going to be the same. Correct? So I can conclude, what can I conclude? I can conclude that what was the result there? If you remember, the sum of all these voltages was 0. So similarly, I can write that here also the sum of these currents is going to be 0. It means what current flows through neutral wire? Zero. Nothing flows through neutral wire. Okay. So in star connection, even if we do not connect this, okay, it is fine. It is not going to make any difference. Understood? Fine. So that is why we will say that if the load is balanced in this connection, we do not require any neutral wire because it does not carry any current. But if the load is not balanced, then neutral wire would carry some current. But we need not worry about that because we are talking about the balanced load condition. Correct? Yes. Next, let us move ahead. Now we will discuss about the relationship between line voltage and phase voltage. Okay. So what is this, the relationship between line voltage and phase voltage? So line voltage is VL and phase voltage is VPH. And just at the starting I told you the difference between the two, isn't it? So phase voltage is going to be the voltage at each phase. So that is measured with respect to neutral. Okay. So that is this. Fine. But if you talk about line voltage will be the voltage between two pair of terminals. So it will be RY or it will be YB or it will be VPR. So now we are going to see whether these two are equal or what relation do they share. Okay, fine. So what we are going to do is we will discuss this phasor diagram after some time. Let us first make the diagram for this Y connection. This. Okay. This is the connection. Now this is ZPH. That is a phase impedance. All impedances are same because this is a balance load. Fine. This is R, this is Y, this is B. Here we have current IR, IY and IB. Okay. This point is R, this is neutral, this is Y and this point is B. Fine. So what is my phase voltage? This is my phase voltage. Okay. But what is my line voltage? I shall use another color so that it is clear. Yes. So this is the line voltage. Okay. This is between, no, this is B. 1 second. Yes. This is B and this is Y. So if I want the line voltage between R and Y, can say this is I'll do one thing. I will erase this and I shall make it again. Yes. So what we will do is we will make the diagram again. Yes, now it is okay. IR, this is B, this is ZPH. Okay. This is R, this is Y, this is N. So this was my phase voltage. Correct? So phase voltage is VRN. But line voltage is this, which is VRY. Got it? Yes. So I wanted to tell you this. Obviously here we have IB and here we have IY. Fine? Okay? Yes. So this I've already written. So we need to remember this point, that phase voltages are this, and in three-phase supply balance condition this phase voltages are same. Fine. Now let us talk about the line voltage. How will I represent the line voltage now? How will I represent the line voltage? Come on, what will be line voltage now? The line voltage will be VRY. Okay, so for your convenience, let me draw that point. Okay, this is, yes, correct. So this is VL, this is RN, correct, this much, and this much is VNY, right, and this much is VL. So we can very well conclude that this VL is nothing but the sum of these two voltages, right? VRN and NY, right? Okay. So what I will do is, I will write that equation. So this line voltage is nothing but the sum of these two voltages. This is line voltage. Please remember this. Okay. So similarly, I will write two more equations. Correct? And the last one between B and R. So I have three voltages which are line voltages. Fine? Okay? Yes. Now we shall move towards phasor diagram. Now how to draw this phasor diagram? So first we need to take any voltage as the reference voltage. So what I will do is, I will take VRN as the reference voltage because R is the first voltage in my phase. It comes first in the sequence. Okay? Now I know that all three voltages are 120 degree out of phase. Correct? So this becomes VYN and this becomes VBN. Fine. Now the second thing is going to be current. Now I will assume the load to be inductive, which is normally the case. Now if the load is inductive, it has some resistance also. Correct? So it lags behind the voltage, right? So this is the current which lags behind the voltage by phi. But why this is not 90 degree? Because inductor will not be pure inductor. So it will not lag behind 90 degree. It has some resistance, so it is lagging by some phase which is phi. Similarly, the Y current will also lag behind. So this is IY. Correct? So this is also phi. Similarly, B also lags behind. So this is B, IB. And again, this is also phi. Now, in order to find the equivalent, the resultant, I have to extend this in the opposite direction. Okay? Why? Because here it is YN. But if I want VRY, what is that voltage? This is line voltage, right? So it was VRN plus VY. NY, right? So I want this NY, whereas this is YN. So it is going to be the opposite of YN. Got it? I'll repeat. I have VYN, but I want NY. Okay, I want NY. So what I will do? I will take it in the opposite direction. Got it? Yes. So this voltage is nothing but VNY. Similarly, what I will do is I will extend all the voltages in the opposite direction. So this becomes NR. Similarly, this becomes VNB. Fine. Okay. Now I will calculate the equivalent. Now equivalent will be the resultant of these two. So this is the parallelogram. Correct? Yes. So this is VRY. Similarly, here also I have to take the resultant. Okay? And same here. Fine. Got it? So this is how phasor diagram is drawn. Now this phase shift is 60 degrees. We have to remember this. Okay? Even this phase shift is 60 degree and this phase shift is also 60 degree. I hope you understood this. Okay? Now we will be calculating the resultant. Now in order to calculate the resultant, I have to apply the law of parallelogram. Okay? Now what is the law of parallelogram? In order to calculate that resultant, I have to take the square. Okay? So individual squares plus twice and the cos of the angle between these two voltages. Okay, correct. So what is the angle? 60 degree. I just told you that this angle is nothing but 60 degree. So we shall be putting the values. Cos 60. Fine. But then what is VRY? What is VRY? It is line voltage. And what is VRN? What is VRN? It is the phase voltage, right? Similarly, VNY, phase voltage, correct? So we will replace VRY by VL and these by VPH. So the new equation becomes VL square is equal to VPH square plus again VPH square plus 2 VPH multiplied by VPH into cos 60. Okay, what is cos 60? 1 by 2. So VL square comes out to be, after multiplying this also becomes VPH square. So we have 3 VPH square. So what is the line voltage? After taking the square root of this, we get line voltage is root 3 times the phase voltage. Please remember this. This is a very important equation. In star connection, the line voltage is root 3 times the phase voltage. Okay, this is very important. Then line voltage leads by 30 degrees to the respective phase voltage. How did it come from? From this. sorry, yes, so it came from this point because this voltage is 60, so this is twice, so individual phase will be 30 degrees. So what is the first point important? This equation, that line voltage in star connection is √3 times phase voltage. The second important point is the line voltage leads by 30 degrees as compared to the phase voltage. There is a phase shift of 30 degree between line voltage and phase voltage. Got it? Now let us talk about line current and phase current. Now if you talk about star connection, now I have connected resistor, okay, let this be anything, but this is a kind of series connection, right? Because only one end is connected together, so this is a kind of series connection, and I know that in series connection the current is same. It means in this connection line current and phase currents are same. So in delta connection the line current and phase currents are same. Important. Fine. Okay. Now let us calculate the power. Now since here 3 phases are used, so whatever power we used to get, okay, this is the power cos phi, correct? This is the power for one phase, but since we have 3 phases, this has to be multiplied by 3. Okay, fine. But when I place the value of phase voltage with respect to line voltage, I get, what will I get? I will replace phase current by line current, and I will replace phase voltage in terms of line voltage. Okay, so I get 3 into VL by √3 into IL cos phi. So this √3 gets cancelled by this, so we get power is equal to √3 times VL IL cos phi. This is again important. Remember what is phase? Phi here. Now phi is the phase between the phase voltage and phase current. Even this is important. It is not the phase difference between line voltage and line current. It is the phase difference between phase voltage and phase current. Okay, fine. So what are the important points we discussed here? That we can connect it in 2 ways. We can connect 3 phase voltages in 2 ways. We will be discussing the summary in the next lecture with star and delta connection together, but I am telling you in short here, we have 2 types of connections. One is the Y connection and another is the delta connection. Then we discussed star connection here, and in star connection we said IL is same as IPH. It means the line current is same as line phase current, but phase voltage and line voltages are not same. So line voltage is √3 times the phase voltage, or phase voltage can be given by this. Okay, so with this we end today's lecture, and in the next lecture we will discuss about delta connection. Thank you.